Hello friends, I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A BE in civil engineering from National Institute of Engineering Mysore, a MTech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed. Having understood how various effective length parameters are to be assigned in a Staad Pro model with the help of a physical model in the previous section, we will now go to the Staad model and assign the required design parameter one by one. So this is our Staad model. Now let us right click on the screen, select level, structure, put radio button section outline 1, apply. So the isometric view of the columns can be seen now. So now we'll know from this isometric view which is the local z-axis and which is the local y-axis of these members. So before that we need to assign the other parameters like yield stress parameter, ultimate stress parameter. So let us go back to level again, select structure tab, select non-radio button, apply. Okay, so now let us go to the design tab on the left hand side. So in the drop down box you will see on the right hand side there are IS 800. You can see IS 800 here. IS 800 2007 is being seen. So now this parameter 1 will automatically come from the template. Now select this parameter 1. Now define parameter. Now let us add FU 490. Usually for plate sections available in the market, the ultimate stress is 490 Newton per millimeter square. So it is 490 kilonewton per meter square. Add, then go to FILD. This is the yield stress. So in Indian code, the plate strength is given as 350 Newton per millimeter. So usually it is being taken as 345 Newton per millimeter square. So write 345 kilonewton per meter square. Add. Then the next parameter is STP parameter. In the STP parameter, you will see two options: hot rolled and cold rolled. Select hot rolled and welded sections. Select welded sections. Then add. Then there will be some standard hot roll section for that. So you have to still define some other yield strength parameter. Go to FU again. This will be now 410 kilonewton per meter square as per IS 800 2007. Add. Then FILD. FILD is 250 kilonewton per meter square as per IS 800 2007. But when you purchase these things in locally, usually we get 240 Newton per millimeter square. So we'll add 240 kN per meter square as another parameter. So add. So scroll down. Now you can see all these parameters here. Now let us select all the built up sections. Go to select by specification, by property name, same. Go to select by specification, property name. This ISMB, whatever ISMB there, we shall change them to built up sections. So these are the sections. Now go to view selected object only. Now scroll down again on the right hand side. Select FU0491. This staircase also has to be deselected. Go to select again, select by specification, property. These are water roll sections, standard ISM sections. So select ISM 250. Then select by inverse. Now go to view selected object only. So now all these sections are built up sections which is available in the view. So let us assign FU is equal to 490. Select FU is equal to 490. Select 490 kilonewton per meter, 490 Newton per millimeter square. Then select the model. Then click assign. Then FILD select 345,000 kilonewton per meter square. Select the model. Assign. Then STP2 is for built up sections, that is welded sections made out of plate. Select STP2. Select all the model, the entire model. Then click assign. Then let us go to FU 410,000 kilonewton per meter square. Now go to view. Whole structure. So whole structure is visible now. Again, now we'll select whichever member is hot roll member. So select by specification, property name. Select 5 sections, 100 MB. Then 100 for tube section, tubes sections. Then all the other 5 sections. Tube sections, 5 sections, and then ISMC 250 also. Now go to view selected roll. These are all standard sections. So usually these sections are available in 250 Newton per millimeter square, but in market the available section strength might go below that. So it is better to take 240 Newton per millimeter square as yield strength. So FU will remain 410,000 kilonewton per meter square. Assign. Then let us go to FILD. FILD will become this is I have taken as 250 Newton kilonewton per meter square. Let us change this to edit command 240 kilonewton per meter square. Modify. It is modified now. Scroll down again. FILD is now 240,000 kilonewton per meter square. Now select all this hot rolled member. Assign. So with this our strength assignment is complete. Now let us go back to the model again. View whole structure. So let us go to 3D view level. It is not exactly 3D view, outline view of the sections, structure, then section outline, then apply. So this is now we shall assign the effective length parameter of each of this member one by one. So our center to center distance for this first column 3.125, then for the second column 3.88. So Our base is fixed. About this direction, but it is not fixed about this direction. So on the top, this member is providing fixity. There will be stiffener plate here. So our LX parameter will be 3.125. So go to parameter, select parameter, define parameter. LX is equal to 3.125. Add. Select this member. Now to minimize our work, we shall assign this 3.125 as effective length parameter for all the columns that are having 3.125 as their effective length parameter. LX as their 3.125 as their LX. We shall assign LX as 3.125 parameter to all the columns which are having same parameter at one go. So let us clear the drawing. So we have this one, press Ctrl and select this one. This has a tube. This has a tube which shall be provided end plate. So we will provide torsional resistance here. Then this one also. So select that. This one. The interior column also will have LX as 3.125. Then the gable column on the other side, and then this column will also have LX as 3.125. This column 3.125. I already discussed that this landing beam is having cleat connection, so with the frame, so this will not be able to provide torsional resistance with the cleat. So the LX will be 3.12 meter for both of these columns. So let us assign 3.125 meter for this column. Okay, we have assigned. Now let us see which are the members which are having 3.125 meter as alloy. See, there is a basing here, there is a basing here. So in this direction the building is non-sway, and for these columns also building is non-sway. So we have alloy as 3.125 meters, that is 1L. This about YY direction, they are all released, they are not fixed. So pinned at bottom, pinned at top, these members are having cleat connections. So pinned at top, so effective length will be 3.125 meter. So, and for this column, Y direction is this, not fixed, but these two frame and Raptor is functioning as a portal frame. So this will provide resistance to this column. So even this will have 3.125 meter as Ly. So let us define Ly. Go to define parameter. Ly 3.125 assign. Okay. So our Lx is assigned and Ly is assigned for the bottom column. Now it is the Lz which has to be assigned for the bottom column. Clear the drawing sketch. Now let's see which are the column that are to be assigned with Lz parameter bottom string. This is the column 1, 2, 3, 4, 5, 6, 7, 8. Actually, for this column at landing beam, the Ly parameter will be 3.125 divided by 2. 3.125 divided by 2 is equal to 1.56. So let us go to Ly parameter. The wall is selected. Now select these two columns. Okay. Now select Ly 3.125 is already selected. Now click on toggle assign, then click on assign. So assignment is clicked. Now we have to define for these two columns Lx as 3.125 divided by 2. 3.125 divided by 2 is equal to 1.5625. That is 1.563 we can say. So define parameter Ly is equal to 1.563. So this landing beam is able to provide restraint about the y direction for the columns. It has a cleat, so we can define Ly as 1.563 for these two columns. Now we have to define the Lz parameter for all this column. So you see all these frames are sway frame. This is a gravity column. When you consider this direction, that is x direction, this is the gravity column. This is a sway frame. This. This is a sway frame. This is a sway frame. Moment resisting frames are called sway frame. This will act as a gravity column in Z along x direction, along this direction. This is again a sway frame. This is again a sway frame. Now see all these columns, almost all these columns are having bottom fixed and top fixed in the direction of sway. So this is top fixed, bottom fixed, 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 this is top fixed, bottom fixed. But for this column, here the connection will be at this point with the flange with the help of cleat. So for this, top is not fixed, not fixed. Not fixed. And for this column, you see there is no restraining member here. There is no restraining member here. No restraint. But there is a restraint at the top. Through the basing, the forces will travel to foundation. So for this column, the LZ parameter will be 1, but for the whole height. So what is our height? Our height is 7.605. So for this column we have 3.125. So for a sway frame with top fix and bottom fix, the effective length factor is 1.2. So 3.15 3.125 into 1.2 is equal to 3.75. So let us see assigned LZ as 3.75 for all the sway columns at bottom story. So define parameter, select LZ 3.75, add, close it. 3.75 for this column, 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 and this column. So our LX, LY, LZ parameter is defined for most of the column. Now remaining columns are these columns. So this is bottom fixed but top hinge. So effective length factor is 2. So 3.125 into 2 is equal to 6.25. So for this two column, effective length in Z direction will be 6.25. Select this column, go to define parameter, LZ 6.25, click assign. Now for this column, as we told, for this column the LZ will be entire height, but effective length factor will be 1. So entire height is 7.605. So let us assign to this column $7.605. So go to parameter, scroll down, select parameter, define parameter 7.605. LZ is equal to 7.605. Add, assign. So our LX, LY, LZ parameters has been already defined for the bottom story. Now you see the Staad actually takes node to node distance for as effective length if we do not define explicitly the effective length for any member. So for all these columns, there is no node in between so in actually speaking, we do not need to define LX parameter, LI parameter for this column because they are all LX is 1 because they are listed at top and listed at bottom, and LI is 1 because there is a frame restraining at top as well as bottom. So LI will be 1. For this column, LI is about this direction. So there is a restraint here and restraint here, but both are hinge, but this column is being restrained by the top. So LI for this column also remains node to node distance. So we will only define the LZ parameter for all the columns in upper story. We do not. Even for the lower story, we could have done it, but for the sake of your understanding, I have assigned the LI and LX parameter also. So let us clear the drawing. So let's see what is the center to center height. For this column it is 3.88 meter and for this column it is 4.88 meter. So 3.88 meter into 1.2, 3.88 meter into 1.2 is equal to 4.656. So we can take 4.66. So let us select all these columns. 1, 2, 3, 4, 5, 6, 7, 8. Sorry, not this column. 6 columns. 6 columns will be having LZ parameter as 4.66. So go to define parameter. LZ at 4.66. This we do not. This we shall not assign 4.66. So define parameter LZ as 4.66 assign. Now for this column LZ will be 3.88 into 3.88 into 2. 3.88 into 2. So 7.76. So 7.76. So let us go to this command. Define parameter LZ 7.76. Now you have to see one thing also. Let us consider the whole height of this building, whole height of this column. This is 7.005. 7.0, so it is bottom fixed, top fixed. So 7.06 into 1.2, so 8.47, so 472. So we cannot assign 8.4. We need not to assign 8.472. We have a better factor here, which is less than 8.472, that is 7.76. So this way also we should always check, so that we design a optimized member and we do not assign effective length parameter as too conservative. So for this column we have already assigned, for this column the LZ will be whole height, so that was already there. So this has been already assigned, so we do not need to assign. So assignment of effective length parameter for all this column is over. Now let us come to the beams. Now see, this is a small model. If I choose only this part and view selected members only, let us move this. We can see all the frame, all the beams, how they are connected, how they are not connected. But for the cases where the model is very big, we might not be able to see this way. We will be able to see only the plan view. So in Staad, unlike in ETAB where the columns are actually shown, in Staad columns are shown as node in plan view. So column sections, if I cut one section here or select one section here, say let us cut this section through 11 tool, go to tool, cut section, exit plane 11. Now see if we see from the top, we do not know where is the column. Now to overcome this problem, the way out is view whole structure, select member parallel to Y, or view. Now these members are a column. Now let us go to support, general support. Let us create one support, fixed support, say okay. One fixed support has been created. So select all this node from one of the elevation view and assign view whole structure. Now go to view whole structure. Now if you come cut section through node 11, exit plane node 11. Now see, we know where is the column. This support will delete before we give a run to the start file. So now these plates are also seen, so we do not want to see this plate. So select all the member. Now go to view on a selected node. Now only the joist and the beams are selected. So as I told you before, we usually take LZ as inter length of these members. So we have for this member LX and LY will be joist spacing. Sometime we might put some node in between, so to change the section sizes, so it is better to define LX and LY for this column. So for these beams, so these beams, and these beams. Now go to design again, parameter, define parameter, LX 1.5 assign, LY 1.5 and these are the joist spacing. So now for this column, this beam, this beam, this beam, and this beam, this beam, and this beam, LZ is 6 meter. Define perimeter, go to LZ 6 assign. Now for smaller span beams, actually defining LZ is most of the time it is not required, because see the compressive strength or bending strength is being governed by a parameter called slenderness ratio, that is called root I by A. Now IZZ by A is not the minimum one. It is for a beam, it is IUI. I is the moment of inertia of the local axis. IUI by A, which govern the strength of a beam, bending strength and compressive strength of a beam. So even if we do not define LZ parameter for a smaller span beam like 6 meter or 7 meter or 8 meters or 4 meters, it will not cause much problem. So now for this beam our LZ will be 4.8 meter. Define LZ is equal to 4.8 meter. Add meter. We are not defining any LXLI parameter for this beam. No distance will be taken itself. So LZ parameter we can define. See, there are nodes here. So LZ parameter, LXLI parameter has to be defined. For these beams, we have to LX, LI, LZ. Everything will be 4 meter. For this beam LX, for these 3 beams LX, LI, LZ will be 4 meter. LX is equal to 4 meter. Assign. LI is equal to 4 meter. Assign. LZ is equal to 4 meter. Assign. Now, only for this beam LZ will be 4 meter. Now all these struts will have, there is no node between, so we'll have LX, LI, LZ as same as their distance, so we are not going to assign it. Staad will treat node to node distance as their LX, LI, LZ. Now let us go to the landing beam. View, pole structure. Select the frame containing the landing beam. View, go to 3D view. Remove the distance. See, these are the points where the stringers are connected. So LX and LI will be taken automatically by Staad. So we need to define only the LZ parameter, which still remains 4. So go to view again, pole structure. Now we have the raptors. For these cantilevers, we can define effective length parameter, but for this small cantilever, we really do not require to define it. We can leave it as it is. But as per code, it could be 1.5 or 2, depending on the restraint here, depending on the restraint that is getting here. So restraint is, there will be purlin here, so that will provide simple restraint. Accordingly we can define the effective length parameter, but it is for such a small cantilever really doesn't matter. So we can take LZ as .03 for all this adapter. Ely and Lx will be defined by the intersection points of the nodes, so we are not going to define them. Node to node distance will be taken automatically by Ely and Lx. So let us select all these adapters and define LZ as 6.03. Sorry, Control Z. So Control Z. This has been assigned wrongly as 4. So let us select them again and let us go to toggle assign. Toggle assign select LZ for toggle assign. So assignment is toggle now. Now let us define a parameter 6.03. LZ as 6.03. 6.03. Assign. Now let us select all the joist. Select by specification, property name. We had defined ICB 250 as all the joist, and then other simply supported beam. This is a simply supported beam. Again, this is also simply supported beam, which is supporting a deck slab. So we can take Lx and Ly as 0.6, Ly as 0.6, assign. So all these members are having Lx and Ly because there is a deck slab on the top, and the compression flash is always on the top for a simply supported member carrying a deck slab. So now this is the case of effective length parameter when we do not have flange braces. Now let us see what will be the case if we have flange braces, and before that we must see where can we provide the flange braces. Now deselect all the member. Now we know we have some internal dry wall here at this part. So we have drywall at this part. So we cannot provide flange braces here. We cannot provide flange braces here. We cannot provide flange braces here. We can provide flange braces from these directions. So this we can have flange braces. 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 Now this also we can have flange braces. If you go to 3D view, outline view, level, structure, section outline, apply. So we can actually have flange braces from the purlins like this. If the purlins runs like this, so this column can have flange braces, 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 this column can have flange braces from one direction, from this direction. This column there is a drywall, so we cannot have flange braces. This column there is a drywall, we cannot have flange braces. This column we have drywall, we cannot have flange braces. So let us select all those columns for which we cannot have flange braces. So this column, this column, this column, this column, this column, because of staircase we might not be able to provide flange braces here as well. So now select by inverse. View selected object. Now select beam parallel to Y. Clear the drawing. Clear the dimensions. Now all these columns we can have flange braces, but not for this interior column. So let us select this interior column. So select by inverse. Again for this column, we cannot have there is no point in providing flange braces because its direction is such that we cannot provide flange braces. So let us deselect this column also. Select by inverse, beam selection, view selected object. Now all these columns we can have flange braces. Now let us toggle all the LX alloy for these beams. Highlight selected, select 3-1, toggle assign, assignment toggle alloy, toggle assign, assignment toggle alloy, LZ will remain same. So all these columns now will have LX on alloy as 1.5 if our cut spacing is 1.5 meter. So let us go to define parameter. LX is 1.5, assign alloy is 1.5, assign. Now let us go to the raptor. If the raptors are provided with a purlin at 1.5 meter spacing, we can have LX and LI as 1.5 meter for the raptor also as well. So go to full structure, select all the raptors. view selected object only. Now go to parameter. Alex as 1.5 assign. Below as 1.5 assign. See, usually Staad treats that para explicit value given to a beam or column as effective length which has been defined later. So even if we have left LXLI 3.125 at above point for some member, if for these members LXLI has been defined as 1.5 as later state, so Staad will treat LXLI as 1.5 not as 3.125. So view whole structure. So all these bracing members and all these, there is the node to node distance, start member node to node distance will be treated as LXLI and LZ. So we do not need to provide LI LX parameter, LZ parameter for these columns. One part is still left, that is our stringer view. So select go to property, specification, property name, ISMC 250, view selected object. Now for this will carry index lamp, maybe it carry some steps made of checkered plates and angle supports, etc. So for both the cases we can go for LXLI as 3.6 meter, 3.6 meter. LX is 0.6 meter, then LI is 0.6 meter. Now LZ for this member will be this distance. For such a small number, it doesn't matter if we do not define it. So let us see what is this distance. If we click on the node, so this is x is equal to 7.65, and then this x is equal to 12 meter, so 12 meter minus 12 meter minus 7.65 is equal to 4.35. So LZ for this stringer will be 4.35. Define parameter LZ 4.35 SN. View whole structure. With this, we have defined LXLI, LZ for all the parameters. So definition of design parameter is complete. And in next sections, we'll group all these members as column, beam, raptor, and then change these standard sections which I have assigned for the sake of modeling, to make the model easier. We'll change them to built-up sections. All the ISMB we shall change them to built-up sections, and then we'll issue design command and try to optimize the building. See you in the next section.